All right. Give me 1 minute. Okay, so welcome everybody. I was just trying to make sure that I don't forget the name of our seminar, which, since it's our last one of the semester, is important. So welcome to the UBS Cornell seminar on AI and data research. So I'm really very happy to introduce Mike Ludkovski, and he has a PhD from Princeton and is now a professor at UC Santa Barbara in statistics and applied probability. He also directs or co-directs the Center for Financial Mathematics and Actuarial Research. So he has a very broad set of research interests. They include Monte Carlo techniques for stochastic control, the modeling of renewable energy markets, commodities, and environmental finance, the analysis of mortality and longevity analysis, market microstructure, and Gaussian process models for quant finance, which is actually the topic that he's going to cover today. So if you have any questions during the talk, please put them in the Q&A, and I'll maybe interrupt Mike a few times, but mostly we'll be keeping the questions for the end. So Mike, the floor is yours. Very glad to have you.
Thank you, Sasha, for the introduction, the opportunity to be here. So this talk will be has the following structure. I will start with a kind of an overview of GPs, Gaussian processes, which is a very broad ecosystem, and so I'll try to highlight. Well, I'll give a quick overview of what it's about, and also highlight the applications to finance. Really, this is kind of a plug for. We have just submitted a manuscript for a short book. Title is the same way: Gaussian process models for quantitative finance. Joined with Jimmy Risk. That's his photo there. Jimmy is a former student who is now at Cal Poly Pomona. And then last year, I had another review article titled Statistical Machine Learning, some more broader than just GPs, and that was in the Annual Review of Statistics and Application. So the first half of the talk will be kind of an overview and very broad strokes, and then I'll go into two sort of case studies, applications, and I try to specifically pick two applications which are really disjoint from each other, kind of going to the opposite ends of the spectrum of how GPs can be used in financial applications. So the first one will be a paper we had with Yuri Saporita on learning option Greeks, and the second one is on just by myself, was a short paper on stochastic impulse control. And again, these two are kind of picked as case studies of how GPs come up in quantitative finance. All right, so statistical learning is about trying to understand input-output relationships. So there's some input X. So it's always going to be bold throughout the slides. That means it's a vector, so it lives in some RD space. And there's some output Y, typically scalar, but doesn't have to be. And the way we think about this relationship, statistically speaking, is that there's some true response F, and Y's, observed Y's, are noisy samples of F. Typically, the noise is additive. That's not a critical feature. It's just easier to explain that way. So the canonical example why this type of models problems are important for stochastic modelers and financial mathematicians is conditional expectation, where I would like to learn the mapping from a system state, little x, to some expectation of a function of some, there's a stochastic process x, and I have some future time, little t, and I would like to have a expectation of that function g in the future. So again, x lives in some subspace of RD. So we have things like this come up, for example, obviously in option pricing, where the expectation is some pricing measure, but they come up, they're really canonical across applied probability and stochastic models. Learning implies that there's some kind of a data set and you try to learn from the data. What I have in mind when I say data is actually a variety of potential settings, which all happen, at least to me, on a regular basis. So data might mean I have some kind of Monte Carlo runs that I would like to aggregate into a functional map so going from points to functions. So that could be coming from Monte Carlo samples. It could be from actual data from empirical observations. It also could be complicated simulators which spit out a fancy version of Monte Carlo. And I would like to again understand how the simulators behave because they're too hard to understand directly. So really statistical learning is essentially curve fitting. But I put a plus because there's more to it than just the basic idea. So usually curve fitting implies you have some kind of you try to minimize some loss function. And so often what happens in applications I'm thinking about, and I'll describe a few of them, is that the loss function is kind of non-standard. And so least squares, for example, may not be appropriate, or you have to be careful how you interpret what you're doing. The second piece, which is kind of important throughout this topic, is uncertainty quantification. So I don't just want to know what is my best prediction, my best guess about the input output. I'd like to understand some uncertainty bars around that quantity. And I'm looking for something which is data-driven, flexible, non-parametric, but something which is not too rigid so that it can satisfy a variety of settings with not too much fine-tuning required on the modular side. All right, so I will come back to this topic at the third part of the talk, but the one long-term vision I had, and this is what I've been working on for well over a decade at this point, is computational stochastic control and what is a good framework to handle all kind of problems. The basic idea is that we have an programming equation where V is a value function. I have a stochastic state X, I have controls U, and I have some, let's say, reward functions G. I didn't write down this terminal reward, but that's kind of can be subsumed. And so we start with a problem which is multi-period, and we try to understand it by looking at locally at what happens one period at a time. And to do that requires us to have 3 ingredients that they have to handle numerically. These problems are generally too hard to solve explicitly. And so we have, first of all, we have the optimization step, and that will sort of be central in several examples I'll mention. So the optimization step means, do the best control you can right now. So this is often the set A can be quite simple. So this optimization actually becomes easy, and this is the whole logic of dynamic programming. The second step ingredient is the integration piece, which is actually taking conditional expectation given, that should really say TK, given where we're right now, looking into the future ahead. Right? And this is integrating out the external shocks, which I'll generally be calling epsilon, that affect my states. And the third piece where the GPs kind of come in for me is the prediction step, where what I have to plug in on the right-hand side is the value function tomorrow. It's the next step, and that value function has to be validated again at TK plus 1, the next time step. Everything is discretized, just to put it on the computer. But importantly, it has to be plugged in. I have to plug in x k plus 1, which is the realization or the value of my state tomorrow, and that's can be anything depending on the dynamics. And so really I have to learn the whole function V as a function of its input x rather than a few point values. And so to be able to handle dynamic programming, I have to be able to do predictions of value function at unknown states which I have never seen before. So this is so solving this type of problem. This is kind of a generic setting. Specific examples, for example, optimal stopping can be recast in this equation by saying that my action space only consists of 2 choices: either I stop, which gets coded as 0, or I continue, which gets coded as 1. And then in this case, I have a payoff function, capital G, and I have if I continue, I get nothing, and I just have to wait. I'll be talking again towards the end of the talk about optimal impulse, where essentially what happens is that I first decide if I want to do anything or not, so I can kind of continue, or I can impulse, which is a lump action, instantaneous lump action, and then I can have to figure out what's the best impulse to pick. This is my C set for impulses. And of course, continuous control also can, this is what it looks like by default. So the vision for how to handle conditional stochastic control is to do something like regression Monte Carlo. Regression Monte Carlo refers to the Long-Schwarz type method, where you try to learn the continuation value, which is basically the conditional expectation over here. Okay, and then what I do, I point-wise do the optimization. So I pick a few initial x's, and I solve this equation for a few x's. That gives me a bunch of y's. Okay, and then once I have x and y's, I do a regression type logic to get the functional mapping x's into y's. I mean, mapping, yes, x's into not the realized y's, but the expected y's, which is exactly the meaning of the Q function. And so this is the plan is, so that's where the surrogates of statistical learners come in, is that I have to lift up from a few training samples, which means I try a few states and I figure out what is the best to do in those few states by solving this design programming equation over here, to having a general representation of what the value is and what is the best feedback control map. This is U star here, across my full state space. And again, the regression comes in as the learning comes in from the ideas that I'm taking conditional expectations, and then I have the optimization as well. So this is kind of the a large class of problems which are of great interest across quantitative finance from a optimization, dynamic optimization perspective, that fit naturally with the previous statistical learning paradigm.
So, Mike, is there some connection with Q-learning or reinforcement learning here? Because it seems a bit in a similar spirit.
So, right. So I'll have a bit more to say on this later. So essentially, the question is what you get parameterized and what you're learning. So this is taking the kind of the, okay, so I'm going to get this wrong in terms of what's the right name of the technique is, but this is the classical idea that I solve the dynamic programming equation locally a few times, and I'll lift it to a whole functional approximation. The other option is to do what I guess reinforcement learning is usually doing, which is parameterize in some very big space, but parameterize first my potential controls or values, right? So for example, you say a priori, I believe that my value function is, a piecewise linear function, or I say my control is given by a neural network, and optimize that. And so that's the opposite direction, which is you first get, postulate what the form of your search space looks like, and then you minimize, the errors compared to what you want it to be. Versus I'm going the opposite direction, which at first locally I solve the right thing, which is what the dynamic programming tells me to do, and then I interpolate for unknown situations.
Mm-hmm.
But yes, this is quite similar. Again, numerically, there's some differences that are actually turned out to be quite critical, and it is pros and cons. So this is not to say this is the best solution, but this is the one way to proceed.
Mm-hmm.
I guess this is a good place to and this slide kind of alludes to that. So the point of this first 20 minutes is not to say that Gaussian process is the cure-all, and not to bash neural networks, but it's kind of to, I would say there's neural networks tend to overshadow everything else. And I think this is unfair, and again, depending on the domain, this may be true and this may be the right thing to say, but I think in finance, there's definitely space for both methods, or I say both methods because really from a machine learning perspective, these are the two big ecosystems that exist. There's of course a whole bunch of sort of, other statistical approaches, let's say random forests or, linear models or generalized linear models and so forth, boosting and support vector machines and so forth. But, in terms of sort of the newer machine learning paradigms, these are the two big paradigms in machine learning. And in finance, I think there's been a lot of focus on neural networks and much less on GPs. And I think this is trying to even a little bit the discussion and sort of saying, here's a useful toolbox. Is it going to be better than neural networks? I think in some cases yes, in some cases definitely not. But this is worth knowing and trying out. So again, this is really is if you try to sort of read about statistical learning, these are the two large paradigms that are out there right now and that are being actively developed. And the big difference is, sort of conceptually, is that GPs are really designed for medium training sets. Medium, that's in the sense of tens or hundreds, whereas neural networks are designed for something very large and trying to go to sort of infinity into the training set and get things perfect on very, very large problems. Yeah.
A quick question about neural networks, because I'm not an expert either, but there is a moment where they add these softmax functions, and it seems that very often you do end up with a probabilistic, but maybe from a serious probabilist, it's like a fake probability or a sort of like a wrapping of probability. So, often, like if we're talking about image recognition, there's a probability that there's a cat in there, or if it's a large language model, there's a probability that the next word is something or else. But I think that probability is somewhat distorted or a bit, how should I say, it's just constraining something to be between 0 and 1, but not in spirit, not as probabilistic, I guess, as Gaussian processes, right?
Yeah. So okay. So again, I was going to sidestep this topic entirely, but sure, I'm happy to talk on all kind of sort of tangents. So by construction, neural networks have no probabilistic concept in them. Now, what you're mentioning, alluding to, is classification problems. Where the question is posed, sort of, what's the probability that something is belonging to, classified to be 0 or yes or no, or cat or dog. I will not be saying anything about classification today at all, and so I just sidestep this. But so I'm thinking about standard regression type problems, and neural networks just give you a point predictions. There's no understanding that there's some kind of alternatives or error bars coming out. There's been a huge effort to try to make this happen, which essentially comes down to bolting something on top of the basic mechanism. So it always has to be added on rather than being intrinsic, where you'll see in GPs it really is from the get-go. It's always there.
Yeah. Okay. Thank you.
Yeah. So the this picture is supposed to kind of summarize what GPs are about. So the key idea is that GPs try to do curve fitting, and they can do curve fitting both in the setting of no noise, which what we call interpolation. So here I have a very, very minimal example. I have 5 data points. This is the blue dots, and in the middle panel, these are taken to be noiseless. So these are the true values of the function f I'm trying to understand. Versus on the right, these are taken to be noisy, and so therefore I try to smooth or regress rather than interpolate, because I know that these are not exact values. And so this is actually not common in statistics, but having a method that can handle both things exactly the same and very organically, and you can have a mix where you can say some values are exact and some are not, is one key features of GPs. So again, so what we have the true response f, we have the observations y, and we have inputs x. And the basic idea is that this looks kind of like a Bayes rule. So it claims that you do a conditional conditioning equation where you think about the posterior of the function that you're trying to understand given the data set is basically about the likelihood of the data given the unknown function times the prior. Okay, so you have two terms, and as a quick preview, the name Gaussian process will suggest everything is Gaussian, and that's the trick. And so the next slide will have Gaussian condition equations that make this work out. But the way people like to talk about this is called covariance structure, which says that if you know something about what happens at x equals to 2 here, that means you know also what happens around neighborhood of x somehow, but you have no idea what this tells you nothing what's going around x equals to 4, for example. And so the covariance structure captures this statistically or probabilistically, that to what extent is knowledge of information x influences neighbors. Okay, so the classical choice, and it has all kinds of justifications, but for probabilists it's easy to say, well, this looks like a Gaussian kernel, is to say that this covariance is captured by this Gaussian density, which means that there's the influence of this point on neighbors has the usual bell-shaped curve. And so again, that's picking a value for L, which is called the length scale, will tell you how far out this neighborhood extends from X. Okay, so so the prior is here. So these are sort of the way to think about these pictures is that I have here my prior is very non-informative, so I have some guesses how my potential Fs might look like, and then I condition on what I see. Again, in this plot, I condition on 5 points. So there's 5 x's, which are univariate, and 5 y's, which are presented graphically. And then I get out of this the posterior, which are potential F's that might fit this information. And so you can see that I have 3 prior curves transformed through that into 3 posterior curves. And again, depending on my noise assumption, I'll be interpolating. So these things go exactly through the data in the middle, but they smooth out. They do not go through the data points on the right. And then I get, since I'll have a condition equation, I have those error bars, which are naturally happening, tells me the uncertainty about how much I learned about F through that procedure. So how this is set up? Well, this is the Gaussian process paradigm. So that says that I assume that for any number of inputs, I have that the joint of this unknown function F across those n inputs is multivariate normal. And I have some mean function, I have some covariance function. And when I think about covariance function, I have a kernel K, which takes 2 inputs and gives me the corresponding covariances. So this is the covariance of F at X and F at X prime, and mu is just the mean of F. Okay, so I take a Gaussian likelihood. So this says that y is just here. So y at x is just f of x plus epsilon, where this epsilon is normal with mean 0 and variance sigma squared, depending on x potentially. And so that's what this line is saying. And then you just take, so this is undergraduate probability, multivariate normal. If you've seen a bunch of values of for a bunch of inputs x, you have a bunch of y's, which is basically linear function of f corrupted by noise, and you try to understand what happens in some other x star, and the x star can be in sample or out of sample, doesn't really matter. That's the equation you get. Okay, so this equation says I can ignore the mu. The mu is the mean. So this is just shifting things off and by the mean where you expect them to be versus where you find them to be. But the key point is I have this inverse in the middle. This is capturing the influence of all the data set plus the noise. So the sigma is the noise. And then I have the vector here, which is saying that this is how at my predictive location x star, how that location interacts with places where I know what's going on. So the kx star is given here. And so you can see that this is basically sort of saying how affected is what I think is going to be happening at x star, given how far it is from the other x's that I've already seen collected data at. Okay, so this is the posterior mean, and I have a posterior covariance as well. And the classical result says that if I have a Gaussian process prior with a Gaussian likelihood, I'm going to the Gaussian process posterior, so I can lift this to a process, and so therefore I have everything in the functional space rather than just a finite dimensional. So this is the standard Kolmogorov extension saying that I can go from finite dimensional distributions to a full process description. Still just talking about the mean and covariance. So this is the another little illustration. So again, what happens is I have some training inputs here. I have, these are indicated by pluses. So in the top panel, I have 5 pluses. In the bottom one, I have, I think, 40. What I get back are the prediction. So the prediction is the posterior mean. So this is the solid line. So this is M of X. So this is sort of the point estimate. This is the most likely mapping that is consistent with my observations. As well as I get the posterior variance. I should put a square here. So the posterior variance. And this is naturally dependent on my location. And that's why I get the credible bands are varying across space organically. Okay, so that's the two things that come out. And then the third point is, which is, you know, kind of maybe misleading a little bit, but the fact that, right, this is just a formula. This formula, which is just multivariate normal conditioning formula, is the answer, both for my mean and covariance. So in a sense, it feels like, you know, there's not much to do. This looks, I mean, essentially it's equivalent to saying that when you do least squares regression with given basis functions, then you have another matrix formula for how the prediction looks like there. And it's actually looks quite similar. There's also a matrix inverse and a vector multiplication. The last thing I want to mention, right? So I can also do examples. So I have a posterior, which is a Gaussian process. So I can, this is, you know, if I fix any number of predictive locations together, I can take samples from this multivariate normal distribution, and that gives me scenarios. So I can extract not just the posterior mean or the posterior variance, but I can also extract samples, which are the grade curves on the top plot from that idea. So I can actually have you know, joined samples across multiple locations, you know, which will lie within this band 95% of the time, for example. Okay, so what is actually you know, means to train a Gaussian process model? Well, this means, going back to this slide here, is, well, I have to pick mu and I have to pick the kernel K. And typically those are not functions, but these are families of functions indexed by some hyperparameter theta. And so, you know, making these two choices of what the family should be like and what the hyperparameters, you know, how to fit those is actually about what fitting means. Okay, so you can see, for example, here, these are the fitted values, and you can see they're obviously not, you know, round numbers. So this is where the training happened, is to come up with this answer. So I hope, you know, these little sketches hopefully indicate to you the sort of flexibility and non-parametric nature of this paradigm, where you know, this thing can adapt to any kind of data set organically, and doesn't, you know, so here this looks kind of like, this is actually, I think, is a sine curve with some shift and translation, but you know, this thing doesn't know anything about that, and it can recover it you know, pretty well with a few samples. Actually, sorry, there is a truth here. As the truth is the red thing, and you can see that this thing overlaps with the truth. You really cannot tell them apart. So that's quite impressive with you know, 40 quite noisy samples just sprinkled around. Okay, so you know, what kind of kernels should we pick? So there's many choices. Maybe the most famous one, which is not obvious why it's famous, you know, when you first see it, but this is called the Matern family, which is so this thing has two key parameters. It's indexed by this parameter nu. So I didn't write out the formula. The actual kernel with a generic nu parameter is something to do with a Bessel function, so it looks a bit ugly. This is an example, which is when nu equals to 5 halves. So nu equals to integer plus a half is the is a good values to plug in because there's some gamma function floating around. And that's how it looks like for the Mattern 5/2 is the most famous of the Mattern family. It looks like this, which essentially, okay, if you look what's actually happening here, this is a quadratic polynomial times an exponential. So that's the form. This is brackets here. That's the form of the Mattern 5/2. Okay, so this little plot is quite helpful. So if you try to plot this, you change nu, and again, I didn't give you the formula for nu, but you know, you don't know what the algebraically it looks like. But if you plot the kernels, so this says fix x and change x prime, and you really, because this thing here is all about it's stationary, so just about the distance between x and x prime. Those are now in R scalars. Plot those as a function of nu. You'll have always the same shape, which is actually this is the nu close to infinity is the Gaussian kernel I showed you before. So this is a bell curve, and they'll look very similar. And so looking at the kernel is actually not helpful. So plotting this out is not going to tell you what's going on because, as you can see in this picture here, the actual typical f's given from this corresponding kernel look very, very different. What actually happens that for the Mattern family, the new parameter controls essentially the smoothness, functionally speaking, of those functions. So you can see that the red is very, very smooth, the green is less smooth, and the blue one is not smooth at all. In fact, so the smoothness is actually nu minus a half. So for the case of this thing here is actually equivalent to a exponential covariance, which is exactly the Ornstein-Uhlenbeck case. So this looks like a Ornstein-Uhlenbeck sample path, which is not differentiable, but it's continuous. The orange is once differentiable. So the orange is kind of like an integrated Brownian motion type process. The green is twice as differentiable, and the red is infinitely differentiable. And so subtle changes in the family of Mattern kernels give you vastly different behavior. And that's quite convenient because you have maybe some priori guess about what kind of smoothness you expect on your on the answers to be, and so being able to choose that is very helpful. So Mattern is a famous family, but there's many others. So for example, you can have what's called rational quadratic kernels, which are basically so R is the distance between 2 points. So these are all stationary kernels, which only depends on the distance between the 2 inputs. So this is basically a power law. I can have a power exponential, which is I take some powers and stick them inside exponentials. There's periodic kernels, which I'll come back to in a second. So in fact, the kernel structure is very rich because a basic result tells you can add and multiply and essentially compose kernels. And so you can construct, with a few building blocks, you can construct very complicated looking kernels. Also, the fact that you can multiply is very convenient because you can easily make kernels in multiple dimensions by just, if you're okay with separability, you can just multiply kernels across each dimension. And that seems to be, generally is a reasonable approach. So what happens again? So now we essentially, the Mattern is a good example. There's this two controls. So, one, I have this global control, but I can essentially say that I want my, am I looking for a curve fitting, which is, a very, very smooth curve, like, a C-infinity curve. I'm okay with some, quite a rough curve. And rough curves are helpful, for example, when I have my function has kinks and corners and so forth, and it can change rapidly. That's what I need to have a more, kinky kernel. The second thing is I have hyperparameters. So given a family, right, this L here everywhere is the length scale hyperparameter, and that controls the actual spatial smoothness in terms of is my function can have very rapid oscillations, or it can have gentle, almost constant and minimal convexity. And so these are the two sort of choices that I get to control by building a GP model. Coming back to composite kernels, so here's an example. So the true function is it's a black dashed curve here, and this is actually a polynomial with a plus a sign type function. And so the blue dots, there's 40 samples here, and the samples are on purpose only fixed between 1 and 5. So all the data we have is between 1 and 5. And then the question is, how well can you fit? So here, this actually, looking at the data, and maybe there's some sort of structural understandings that this function might have some kind of a periodicity going on. And so there's a periodic kernel which can capture that. And so, if you fit a Maton 5.2, which I was advertising before, this is the blue curve, you get actually a pretty good fit, right? So things look really good. It actually, without knowing anything, it does a good job in sample. But it has, of course, a hard time because since it doesn't have any idea what's going out of range, it has a hard time to extrapolate outside the training range, right? So the blue curve is not capturing the correct behavior. On the other hand, if I take a, this should say really, somewhere should say periodic, but I have a bespoke additive composite kernel, which has a periodic component, then I get this orange fit, which is remarkably well extrapolating beyond the range. So it's really kind of figured out both the behavior of the polynomial component, which is hidden inside, as well as the periodic structure that the data has. Again, just by looking at these 40 data points between 1 and 5. So these things can have actually really good extrapolation power if it's given some help, that there's some kind of structural understanding that the model can provide. Okay, so in terms of time, so let me just quickly go through this. So how does fitting work? So the fitting is really about understanding the hyperparameters. So essentially what happens is we pick some kind of kernel family. So we pick some structure, and then we learn the hyperparameters. And usually this is done by maximum likelihood. So you write down the likelihood of the data given the hyperparameters, and that's a highly nonlinear and often a degenerate optimization problem, and then you have to solve that. The typical method now is use the stochastic gradient descent, and so actually the usual TensorFlow, PyTorch toolboxes get reused for that purpose now. And then the other thing which I just want to mention on the slide is that you can combine the structure, which is kind of designed for when you don't have any a priori good guesses what's going on, with a parametric, essentially detrending. And so you can stick in a parametric prior mean, which if you have some sense of what the curves look like, and you can learn the coefficients beta together with doing the GP conditioning. And so you can do it jointly. This is called universal kriging. And so you can do 2 steps in one, detrend and learn how the detrended shape behaves spatially. Okay, so GPs are connecting to a few different things. So one is quite well-known technique in non-parametric statistics is kernel ridge regression. So kernel ridge regression tries to minimize some kind of a loss function between the data and the unknown functional response by using reproducing kernel Hilbert spaces and using corresponding penalization, which is based on the RKHS norm and again, the RKHS means that I have some kernel functions and I look at the closure of the span of those kernel functions. And so this actually is essentially the same equation as the GP solving, where the lambda gets interpreted as observation noise. And so there's an equivalence between saying that I have a high penalty in kernel ridge regression versus saying I have a lot of noise in my GP equation. Now, KRR is only doing the point estimate, is just figuring out the best possible element of side the my RKHS. And so it doesn't have the probabilistic structure embedded in it, but otherwise it's essentially doing the same logic. And so this is a good perspective because it really highlights the fact that my estimate, my prediction, is literally just a linear combination of those kernel functions. And so this is, it's an element of this reproducing kernel Hilbert space. So it's really spanned by this initial kernels function. So everything, all these plots here are really just a superposition, for example, of my bell curves, my Gaussian kernels, centered at my data points. The other perspective, which is if you stare at the equation here, you can see that this equation actually is linear in the training output. So this is really just saying that my prediction is just a weighted average of my training output. So I'm just averaging out what I've already seen. Okay, and the averaging is based on this. This is a vector, which is basically coming from the contribution of the covariance structure I proposed and the noise. So this immediately tells you why you're going to have this issue of what's called reversion to the prior. So outside the training data, for extrapolation purposes, it's basically going to revert back to what the prior was. And so the data is going to have minimal input when I'm far away, because the weights get small. And secondly, it points out that the posterior variance, which is a nice feature, is independent of the observation. So the whole uncertainty quantification is driven only by the input geometry rather than by what the points are actually what the observations are. All right, so let me move to the next slide in a second. So the only thing I want to point out on this slide is there's many packages in Python, in R, in MATLAB, in Julia that are available and can do all kind of nifty tricks. And so the learning curve is really not too steep in terms of you don't have to code anything yourself. You can stick to high-level packages. And you can see, for example, GPyTorch is probably the most well-known now in Python, and that is, as you can guess, build on top of PyTorch. So if you work with PyTorch, this is really not a steep learning curve. Now, okay, so why would GPs come up financial applications? So let me point out a couple of main areas. And so again, in this book that we have almost done, we had this is each of those things is its own chapter. So from perspective of option pricing and hedging, I'll go into this in the first case study. But this is the basic idea is that traditionally, if I want to do option pricing, I have a formula like a Black-Scholes formula, or maybe I have to solve it. I have a PD solver which can solve my Heston PD, for example. But if I have something more sophisticated, I have to move beyond that, or maybe it gets too slow. And so you want to have a statistical representation of the same mapping from inputs, which may be, for example, option characteristics, let's say strike, maturity, and so forth, into the prices and corresponding Greeks. So I think the first paper was by Spiegler. That was Dilip Madan, Skutins, and forget one more person. This was in 2018. There was a well-received paper by Stefan Crepe and Matthew Dixon, 2020. And then I'll be talking in a minute about our work with Yuri. So that's the first application. Again, this is basically saying, let's replace the usual pricer by a ML tool. And again, this is, it's really is a tight race against, let's say, neural networks have been also used for this extensively. The second idea really is about going back to curve fitting. So if I have a financial object and I would like to fit it in a non-parametric way, then GPs is a natural candidate because it gives you this nice structural, knobs to turn, as well as the uncertainty quantification may be helpful. So for example, if you want to build a yield curve, right? I have a bunch of, I have a 20 points on my yield curve, which I can observe, and I try to interpolate the rest. And I want to have something flexible, more flexible than, say, Nelson Siegel and the likes, and GPs is a nice structure. So there's several papers by Demir Filipovic on this topic. They're mostly using kernel-rich regression, but it really kind of translates naturally into GPs. Similarly, if I have implied volatility surfaces and I would like to interpolate observed bid-ask, let's say, prices, or so forth, GPs is a natural structure that can give you error bars. And the error bars that you get from GPs, which again are input dependent, are helpful because they let you propagate through to say about, let's say, how much errors you might get on the price of exotic options coming out later on. There's folks who worked on Fred Bentley was the first one, I think, historically, who looked at GPs, and he looked at commodity forwards. I have multiple papers about mortality rate surfaces. These are 2D objects. There's a paper by Kuzan and et al. On swaption cubes, which are 3D objects and so forth. But anything which is, flexible financial objects you like to understand and have error bars for, GPs is a natural fit. And then, as I mentioned at the beginning, stochastic control. So if you want to have a representation for expected gain, Q function or value function, the function of current system state, GPs is a nice way to capture this. And so the classic example is for Brilliant options. And when I want to price Brilliant options, I have to decide, do I continue or do I stop? And that's the quotation value. And so I have multiple papers on this. I will also mention that this is actually 2 papers by Good and Nash et al. in Paris. All right, so I'm going to be behind, so let's see if I can speed up a little bit. But the first case study is about learning the Greeks. So if you want to have, if you want to hedge some options, then you really want to know the corresponding Greeks sensitivities. So delta is sensitivity with respect to the underlying, theta is with respect to the time to maturity and so forth. And so, classically, if I have a formula, I can just take derivatives in terms of classical derivatives and get the corresponding partial gradients. But if I have something more sophisticated, then I have to be able to take those same gradients on something which doesn't have a closed form expression. Okay, so people have tried to use both neural networks and Gaussian process for this, and let me try to go through that in the next few minutes. Okay, so there's quite a lot of literature on this topic. It's really got a boost in the last 10 years when people realized that using backpropagation or auto differentiation, I can get things essentially implicitly in any complicated model just by differentiating the code rather than having to do anything by hand. And so that's now built into all the machine learning infrastructure. So I have this tool available, and that's kind of fits nicely with the goal of trying to take derivatives of some complicated function. So here's a setup that I wanna kind of advertise. So I have a bunch of option prices given. So 2 examples are, I have option prices coming from my, I have a model, and the model, it doesn't have a formula. And so I did, I ran my model on a few inputs. Okay, or I have observed data, and these are the observed, let's say, times, strikes, underlying prices, and so forth. Okay, but this is all option prices. So what I do is the plan is the following. I'm going to build a surrogate, so a statistical representation, a Gaussian process model for this option price. So I'm going to, for any input, I'll be able to predict what the option price is. And then I'm going to differentiate this surrogate to get the corresponding Greeks. Okay, now that sounds like a bad idea in general. So in general, if you build a representation for the price, then you are in no man's land, in Wild West, to try to take derivatives yourself. So for example, if you try to do some kind of a polynomial or spline representation for p hat, you do not want to take derivatives of that. You're going to get garbage back. Okay, but for GPs it works well. So here's an example. This actually has 2 examples. This has both the Gaussian process as well as a neural network. And this is a call option. This is actually the vanilla example of a Black-Scholes. So this actually has a formula, but the red is the exact. The purple is the neural network, and the orange is the Gaussian process. And you can see they fit really well. And this is again the delta coming from training something for the price and taking derivatives. Okay. So as I mentioned, there's 2 cases. One is that there's a data coming from the modeler, and this will be typical examples. If you have, let's say, Monte Carlo, so I have some kind of complicated model. I don't know, path-dependent volatility, but I can run Monte Carlo simulations on that. And then so I have a bunch of samples of that, and I would like to interpolate to unknown states I haven't seen before. Or there's a data set with actual, observed market prices. Let me skip this, but this so you know, this is a practical selling point of saying, okay, why do we care about estimating deltas in practice? Well, because if you have a better estimate of delta, you're going to have a better hedging performance, and you can kind of see that the most the naive thing that people might do in practice is what's called implied delta, which is figure out the implied volatility and plug the implied vol into the Black-Scholes delta and use that for hedging. And that has a bias, and so that bias can accumulate over time. And because of the skew gives you the bias, and because of that bias, implied delta can perform badly in many models. And so you have to be smarter than implied delta to do hedging in practice. So why GPs are nice? So this is the kind of the key slide on this case study is the fact that there was a slide in a few slides back. I mentioned the fact that the GP posterior mean is linear in observations, okay, and then and the weights were just given by the kernel. So I can analytically take derivatives of these weights, and that just comes down to differentiating the kernel function, and that gives me the correct answer because everything's linear. So it's due to linearity, I get closed form gradients. And so this says that if I build a GP and I fit it to the prices, I automatically got a GP for the gradients, all the gradients at once for all the Greeks. And I just have to, I can take analytic derivatives of my kernel functions once and for all to get self-consistent estimates as well as bands for all the Greeks, let's say the delta, the theta, and so forth. So this is a slide showing you the formula, but again, basically says that the Greek estimate is just differentiate the posterior mean analytically, and so this comes out to differentiating the kernel function with respect to the corresponding coordinate, and you can also do the same for the covariance, right? So the nice thing is that you can also do that for the covariance, and then you get now the error bars on the Greek. So here's how this looks like. So what I do is I train. So now I'm training in 2D, and I'm plotting things in 1D to illustrate the what's going on. But my training sets are I look at the call options. Okay, so it makes things super simple. Call options in the Black-Scholes model as a function of time to maturity and the underlying fixing strike and underlying initial share price. Okay, so my training sets are Monte Carlo estimates. I do the most naive thing. I run Monte Carlo. I do empirical averages. This is my input data. I do this 400 times. That's quite small. I'll come back to that. And I collect the corresponding empirical averages using and check Monte Carlos at every input 400 times. And that's as in 2D. And then I plot things in 1D, which I change the underlying S. And here's the strike is 50. So the strike this is a strike. And I fixed time to maturity in this plot. Okay, so this is a call option. So the true delta as a function of underlying has this S shape. And again, I'm showing you only the Greeks. I'm not showing you the fit of phi hat itself. I'm showing you the corresponding gradient. You can see things look pretty tight with small error bars and remarkably well. And there's some issues here, which I'll come back to in a second. But the main thing I want to mention is that this is a delta. The delta means what? Delta means I'm differentiating with respect to the second coordinate because my inputs are called tau and s. If I differentiate with respect to the first coordinate, and with a minus sign, that's my theta, and you can see that this is the same GP process, which is 2D, differentiating the other coordinate. And so these two pictures are fully self-consistent, right? They're coming from the same underlying base model. And it's doing well in both coordinates, right? So it's not doing like well in one, but not the other, and so forth. And so that fact that this is consistent, I can have I can have a cross covariance if I wanted to get that as well analytically. So the workflow again is, I specify the ingredients of the GP. I fix a training set. Either it's given to me as data set, or I have to decide what I want to train on. Then I estimate the GP hyperparameters, and then I just basically linear algebra plus a little bit of very rudimentary calculus to get all the Greeks I want, and I get them all at once. So I don't have to do any bumper value. I don't have to recompute anything. I get all the Greeks in a consistent way, self-consistent way across all the potential directions. And the method doesn't care about the payoff. So this thing, I showed you for calls, but I can have any other, I can have, for example, portfolios. I can have a collection of contracts all put together, because this thing doesn't really care what the Ys look like. It's going to take some averages anyway. So it doesn't depend on the payoff structure. And it really does not depend very much on the dimension. So in my example, I said I'm going to learn something as a function of time to maturity and underlying price, but I can throw in a bunch of other factors and go to multi-factor models or more option characteristics. It's going to slow down the learning. So I don't want to claim this is there's no cross dimensionality, but as an implementation, as a thing you have to worry about, it's pretty much scaling as you might expect without any hitch to higher dimensions. And again, I don't want to claim this can go to 50 dimensions, but I don't think everybody has 50 parameters they're trying to calibrate at once. So you have to worry about things like reversions to the prior, right? So you have a problem here. This is a fully statistical method. It has no idea that delta is supposed to be between 0 and 1 and monotone, and so it will try to go back because it has no training data in this areas. It's very honest about it. It tells you that the credible intervals are very large, so it tells you that it doesn't know what it's doing. And so this is a nice self-diagnostic. It tells you I have no clue what's going on here. But if you don't like that, if you want these things to stick, you have to put some kind of boundary conditions. And so we have one trick, which is doing this little fencing here. So we go ahead and we manually add a little bit of boundary conditions, a little fence, saying that the delta essentially is 1 at the edges of our training set to enforce what the pattern we want to see. And this is exactly a nice, clean place to put in some expert knowledge. So we know that the delta should be 1 deep in the money. Again, for example, for neural networks, I don't know how to do that in a clean way. But here it's very clear where to insert this.
Mike, we have about 5 minutes or so. So just to let you know.
Yeah, sounds good. Let me skip this. I want to show you this plot here. So again, kernel choice is an important selection. So if you pick the wrong kernel, you're going to get bad answers. Okay, so now what does the wrong kernel mean? So if you pick something which is not very smooth, Mathern 3/2 only has 1 gradient. So Mathern 3/2 has no good gamma. This is the second derivative. And it also has bad delta because it's not differentiable enough. So this is like a kernel which is too rough. On the other hand, if you pick a squared exponential, this thing is too smooth. And you say, okay, what's wrong with too smooth? Well, it's not as easy to see on this plot here, but for the theta, this is just the Black-Scholes model, but the theta has a complicated shape where it's very nice here. It goes down quite nicely, and then has a very rapid sort of canyon right around at the money, and then bounces back up, but not all the way up. So this is the right shape of the theta, and so the theta has a very sharp, very huge convexity in this area here. And the squared exponential kernel doesn't like such behavior, and so it underfits. It tries to smooth this out, and it doesn't capture the correct, shape here, and so it basically gives you not a great theta estimate. It does well on the delta because delta has a nice smooth shape, but not well in the theta. So you can undersmooth, you can oversmooth, and so this is again requires some expert knowledge and some fine-tuning to figure out the right kernel choice, but it makes a big difference especially for this task of Greeks. And so the paper has a bunch of stuff about what happens if you try neural networks. The answer is neural networks, they work great if you give them lots of samples. So as a comparable performance, this is a picture which is I would say is comparable to the best GP we had. You have to have, okay, this is we had a grid, and so there was a little bit of a handicap here, but essentially you're talking about tens of thousands of samples to get the same fit as with 400 for GP. Okay, now just because it's 20,000 samples doesn't mean it's like much slower. It actually has its running speed is not dramatically less, but it requires way more data to get to learn the same thing, right? So it has a hard time extracting useful information from a data point, whereas the GP does much better. So it's much more flexible, much more attuned to the data rather than the neural network, which kind of say, well, give me a lot of data and I'll do a great job for you. And it actually still has a trouble with the theta. The theta is really tricky to get even for this vanilla example. Okay, so I have 2 minutes. I'll talk about impulse control very briefly. So this is an illustration of stochastic control. The example that's in the short paper I have is completely different topic, nothing to do with what I mentioned before. It's actually about what's called forest rotation. So I have trees in the forest. By default, they grow themselves as a arithmetic Brownian motion. So there's some growth rate mu, and there's some fluctuations because there's droughts and whatnot. So the trees can die off on their own. And that's how lumber grows unimpeded. And then once in a while, you want to harvest them, you want to cut them down. And that means that's an impulse. So you go ahead and you chop a bunch of trees down and you sell them. So once you chop them down, you sell them. This is saying that when you sell them, you have a fixed cost of 1 to pay. But otherwise it's linear. And so if you have linear profit, then if you chop them down, you might as well chop all of them. All of them means, 0, not 0 means no trees, but means, this is a nominal value that you want to restart. And so the problem becomes, when should you chop trees down? How far you should let them grow to maximize your overall discounted revenue. So this is a problem again, where what matters is you have some kind of an impulse cost, which tells you what happens when you act. Otherwise, you have some running cost, which is the business as usual situation where you don't actually act, you just wait. And so the dynamic programming looks the following. It says you're going to get your running reward no matter what, but otherwise you have a choice. Either you do nothing and you get your look ahead value from the next step. This is the Q function. Or you go ahead and you do the best intervention, the best impulse you can. That's called the M operator, which is maximizing over all possible actions what to do. And the action means that you move X instantaneously to X plus Z, and you pay a cost impulse called kappa. Okay, and so the whole point is that to solve this equation here, okay, you have to see, okay, what do I have to know? Well, I have to learn these two things on this is given to me, G is given. I have to learn the Q function, Q, which is a conditional expectation. And I have to learn the function M. M is optimization of the Q. Okay, and so the natural thing to do is, well, the Q is the immediate object to learn. I can put some kind of a regression, Monte Carlo type logic, so I can put any kind of regression model, anything from neural network to a Gaussian process on it. And then I have to be able to do M, which means I have to optimize this statistical function Q, which becomes Q hat, in terms of Z. And so, of course, to do this optimization, the logic should be, well, you want to take some gradients of your Q. So this becomes a Q hat. This becomes an M hat. And to do this, you really want to do it like using calculus. You don't want to take the soup by hand, numerically, but you want to take derivatives of Q hat with respect to the second component, derivative of your kappa, which is given to you. And then you want to figure out what is the best action to take if you want to intervene. And so that suggests you want to have a statistical learner for Q. Yeah, and this is the main thing, which is conditional expectation, where you can do gradients in a nice way. And this is exactly what I just talked about for the Greeks. For the Greeks, I want to take gradients because I was trying to do hedging, and that was the right thing to do financially. Here, I want to take gradients because I have a soup of the unknown value function, and I want to do that as analytically as I can. So I want to write down the first order condition rather than having to do let's say a line search. And so here is let me skip this, but this is the basic idea: is that you simulate some trajectories, you figure out the corresponding costs, you collect them, and you have inputs X. This is your training inputs. You get some sample training outputs Y, and then you build a surrogate, which can be anything you like. It can be a quadratic function, but you want to have something flexible and with good gradients. And so you want to build, for example, a GP, and then you can use GP gradients to compute the corresponding impulses and impulse maps. So this is a plot where, so this is a time-dependent forest rotation problem. This is the So in this situation, there's a formula for the infinite horizon solution, and these little dots tell you this is the you should think of this as years. And so these are the estimated cutting levels of your forest in given the year, and given they have 50 years total to go. And so you see this, the correct answer should be like a smooth curve going like this. And so whatever noise you see, this is a numerical instability, but otherwise, given that the scale, in fact, is this thing is only within plus minus 0.005, so it's actually remarkably accurate without any extra fine-tuning on my part to figure out where it should cut this forest down. All right. So to conclude, so GPs are, I think, a useful part of the machine learning toolbox. There's many applications. This is still kind of in the early stages, so there's many more papers I'm sure are going to come on this topic. And then if you're interested in what some of the things I showed, then they're not public yet, but they're going to be public soon, multiple Jupyter notebooks where you can fully reproduce multiple of the plots. And some of the plots I showed today, more plots in this forthcoming book, and a variety of applications. And I have many references because I covered a lot of ground. Thank you. I'll stop here. You're on mute, Sasha.
Thanks. Well, it's a lot of potential avenues for applications. I really like that you gave us a little background on GPs and how they fit in the arsenal that students should have on how to basically fit through data. I'm a bit curious. I mean, we should probably stop the recording, but is there any notion of no arbitrage in these option pricing formulas, or is there a risk that a Gaussian process might lead to some arbitrage violations?
Okay, so by default, this is doing statistics with pretending you have no idea what's going on. So this has no notion of what there's nothing built in a priori. Right. And so yeah, this is just doing curve fitting, right? So this is this picture kind of says,
which is true of any technique of that.
Yeah, but this is saying you can actually do pretty good curve fitting, which gives you all the you can fit curves well enough. You can get multiple Greeks for free essentially. That's all this is saying. Now is this good enough for practical use? Probably not. So then you have to say, okay, which part you don't like, what do you want to add in, what kind of information you want to have. We say you want to have an arbitrage, for example. You say, well, I would like my my surrogate p hat for the prices to be I don't know, monotone, convex, right? Let's say convex in the underlying.
Yeah.
Right. So and so that's same thing as saying you want your delta to be monotone increasing, let's say, for the call. That's a constraint, right? That's now saying you want to have a convex p hat. So the short answer is convex, shape constraints on any curve fitting is a nasty problem which we have not been able to solve, and I think it's unlikely we're going to have a good solution ever. So in every framework, this runs into all kind of trouble. So GPs are not exceptions. So constrained GPs is ongoing project, but again, there's no easy fix. Now, one fix which has been successful, and so Areski Kuzan worked on this in France extensively, and he has nice results. Is it's a constrained GPs is bad because GPs is a functional object, and constraining functions is bad, and these functions want to be supported on the full real line. So if everything's Gaussian, so constraining Gaussians is known to be a bad idea. But if you can reduce this to a finite dimensional problem, then it's okay. And so one fix is to say to you what's known as a finite dimensional GP. So you go to a finite dimensional representation. So you a priori restrict the degrees of freedom you have. You hopefully make it large, but you restrict that, and then you end up with a finitely many constraints to look at, and that becomes essentially, in a nutshell, is like saying I have a high-dimensional Gaussian random variable, and I want to look at its, in an orthant where it's all positive, for example. And that's tractable. This software can do that for you efficiently and quickly, and so you can have a good solution in this finite dimensional approximation. Now, by doing this finite dimensional approximation, you lose something else. So it's not a free thing to do, but that exists, and there's there's references on this, and this has been done. And in fact, there's the paper I mentioned about the swaptions. Where did it go? It's here. This paper, it's even worse because for swaptions you have this triangle constraint. So it has a calendar spread constraints. There is a time time constraint, but also there's a third in the tenors. There's a triangle inequality, which is even worse because it's a weird looking thing. But they figured this out how to code that up in this 3D object, which is quite nasty because it's pretty much all the software only can handle 2D settings, and so going into tensors becomes a ugly exercise in coding. But they managed to handle that again using this finite dimensional approximation. There's other tricks, for example. So there's many papers, and there's more coming out on monotone GPs. So monotonicity is something which is easier to handle than, let's say, convexity. And so there's all kind of approximate solutions how to make sure that your fit is monotone. But yeah, I mean, again, the starting point is this is a curve fitting exercise, so there's no prior on anything, but you can impose things along the way, and again, you can sort of decide you want things to be a hard constraint, soft constraint, or one thing with GPs because you can generate samples, and so you can say, well, I can just do some kind of a acceptance rejection, with some adjustment for that, but saying, well, if I get something which doesn't look good to me, I just throw it away and try again.
Yeah.
But monotone neural networks is also a troublesome object, so I don't think.
Absolutely. I mean, I even think the advantage of having a real probabilistic structure underneath it is very comforting to me. So that the way these curves sort of get fatter towards the edges or in parts where they're more uncertain, that I find that very how should I say, comforting. It makes me think that maybe if language models had this kind of thing, we would be more aware of when something like a hallucination is happening, or something that where there's not a lot of certainty about the truth of a statement.
Yeah, so I mean, again, and it can go in different directions. So because I'm looking at the slide again. So so Damir has a paper with I think it's Marcus Pelger. It was look at yield curves, and for yield curves, of course, right? It's you have to expect that the yield curve, the discount factor is decreasing. It cannot be negative. It should not be negative. So that's a monotonicity constraint. So what they figure out, they come up with a very special kernel, which is kind of pre-engineered, and so they lose some degrees of freedom on that. But they essentially a priori figure out a trick to guarantee there's going to be decreasing, some transformation and so forth. But that's the solution, which is they do for yield curves, and that's it's a different direction to try.
Okay, well, Mike, thank you very much for. We've got one Q&A. Just someone saying thanks for the presentation. So thanks again, and yeah, goodbye, everybody. We'll see you in the fall.